Section 9.2 is on infinite geometric series. For the warm-up, label the following as arithmetic or geometric, and then decide if it's a sequence or a series. So for the first one, you should have noticed that it was geometric. It's geometric because it has a common ratio. To find the common ratio, take any term and divide by the term before. So here the common ratio is multiply by -2. This is a list of terms, so this would be considered a geometric sequence. The second one is arithmetic. You can tell because it has a y-intercept of 2 and a slope of 3. You're adding 2 every time. And it is a series because we're adding up from the 0 term to the 5th term. So this is an arithmetic series. Series is a sum of terms. Let's review arithmetic series. We looked at Gauss's formula, and this is Gauss who added up the numbers from 1 to 100. You found that pattern. And to review that pattern, to find the sum of any number of terms, you take the first term plus the last term, multiply by the number of terms, and then divide by 2. So there's Gauss's formula. This is what we went over yesterday, and we solved multiple problems using Gauss's formula. Today we're going to look at, again, geometric series. So let's take a look at the first problem. You bake a delicious pie and you eat 1/2 of it. Determined to make the pie last, you decide to eat only 1/2 of the pie that remains each day. Fill in the following table, leave answers in fraction form, look for any patterns. So on day 1, you bake the pie, you eat half of the pie. On day 2, you eat half of the pie, or you multiply 1/2 times the 1/2 and you get 1/4. On day 3, we multiply 1/4 times 1/2, and we eat 1/8 of the pie. On the day 4, we'll eat half of 1/8, which is 1/16. On day 5, half of 1/16 is 1/32, and so on. Okay, let's look at total amount of pie eaten. So on day 1, we've only eaten half of the pie. On the next day, we eat 1/2 plus 1/4, and 1/2 plus 1/4 is 3/4. On day 3, we eat 3/4 plus 1/8. That would give us 7/8. On day 4, we eat 7/8. Let me rewrite that, 7/8. Plus 1/16, and that would give us 15/16. So if you've noticed a pattern, the denominator of total amount eaten is the same as the amount eaten that day, but the numerator is 1 less than the denominator. So this would be 31/32. Day 6 would be 63/64. Day 7 would be 127/128. So already by the first week, you've eaten almost all the pie, 1/27 out of 1/28 of the pie. If you live forever, how much pie will you eat? Will you eventually eat the whole pie? So you'll eat almost the whole pie. Vocabulary for today. A geometric series is the sum of a geometric sequence. An infinite geometric series is a series with infinitely many terms like the pie problem. We could just keep multiplying by 1/2 every time and it would keep going. A convergent series has a long-run value or an asymptote. We looked at this in section 1.3. Long-run value, a limit, an asymptote. A convergent infinite series has an equation to help us figure out the sum, and here is the equation. The sum is the first term over 1 minus the ratio. So if you have a convergent series, something with a limit, we can add up all those terms and actually find a sum for that, even though it's supposed to be going on forever. For example, the pie problem. So for the pie problem, the first term on the first day, we ate half of the pie. The ratio is 1/2. We're multiplying by 1/2 every time. So the sum is 1/2 over 1 minus 1/2, which would give us 1/2 over 1/2, which would give us 1, a sum of 1 pi that you would eventually eat. So it converges to 1 pi that you would eat. Let's take a look at a few more examples. How can you tell if a geometric sequence is convergent or has a limit? Well, you look at the ratio. If the absolute value of the ratio is less than 1, it will be convergent. So here's an example. This is a geometric sequence. To find the ratio, take any number, divide by the one before. For example, 1 over 5. Let's try that again. 1 over 5 equals 0.2. So you ask yourself, is this convergent? Is 0.2, the absolute value of 0.2 less than 1? And it is, so it's convergent. What that means is we can use our sum formula and we can figure out what all of these sums would add up to. So let's try the next one. Figure out the ratio. So this is a ratio. Take any number, divide by the one before. 80 divided by negative 40 is negative 2. Is the absolute value of negative 2 less than 1? No, so it's not convergent. It would not have a limit. It would not add up to something, and you could not use the sum formula. So again, all these terms would add up to something because these numbers approach 0. But these numbers would not add up to something because the numbers keep going. How can you tell if the series is geometric and infinite? By looking at the sigma notation. It's geometric if you have a ratio. So here's our ratio. It's infinite if we have this infinity sign right here. And we know this is going to be convergent. Look at the ratio. The absolute value is less than 1. So you can actually find the sum of this by doing our first term over 1 minus the ratio. So here the first term is 0.3. The ratio is 0.1. So here's the first term, the ratio. And if you calculate that, that would give us 1/3. So if you were to list out all these terms and add them together, since the ratio is less than 1, your terms are decreasing and they get closer to 0. So you could add them together and you'll get a sum of 1/3. Here's another example. This is geometric because of the 0.25. It's infinite because of the infinity sign. It's convergent. Our ratio is less than 1. So let's find the sum. So we have first term over 1 minus the ratio. First term is 2. Ratio is 0.25. So we get 2 over 0.75. And that gives us 2 2/3. So if we add up all these terms of the geometric sequence, it would eventually add to 2 2/3. That would be your limit. That would be your sum, I should say, not limit. Okay, solving different types of problems. The first term of a geometric sequence is 60, and the sum of the series is 75, so we know it's convergent. Find the common ratio of the series and list the first 5 terms. So first step, plug into your formula. We know the first term, we know the ratio. We don't know the ratio, we want the ratio. So the sum is 75. That equals 60 over 1 minus r. Well, since we have the 1 minus r on the bottom, and I don't want it on the bottom, I could cross multiply. So if we cross multiply, we get 60 equals 75 times 1 minus r. We could divide each side by 75. And we get 0.8 equals 1 minus r. Solve for r, subtract 1 from each side. We get 0.2, negative 0.2 equals negative r. Divide by negative 1. So r, the ratio, equals 0.2. It should be less than 1 if it's convergent. All right, find the first 5 terms. So in your calculator, I would do this recursively. 60 is the first term. Multiply each term by 0.2, so the next one would be 12. The next term would be 2.4. The next term would be 0.48. And the last term here would be 0.096. You can see these approach 0. Next part of the lesson, have you ever wondered how to write a repeating decimal as a fraction? Well, wonder no further. Here are the steps. Step 1, identify the first term of the common ratio. I wonder if I can take a screenshot of this and move it up. Okay, here we go. So to do that, I'm going to rewrite this as a list of terms. This is 0.36 plus 0.0036 plus 0.00036, and so on. So this is actually a geometric sequence. The ratio would be any term divided by the term before it. And so here the ratio is 0.01. So we can plug into the sum formula. We know the first term and we know the ratio. So the first term is 0.36. The ratio is 0.01. That becomes 0.36 over 0.99. And if you reduce that fraction, that's the same as 4 out of 11. We could divide each of the terms by 9. So 4 out of 11. How about the next one? 0.4 could be, or 0.4 repeating could be written as 0.4 plus 0.04 plus 0.004 and so on. So to find the ratio, take any number, divide by the number before it. So 0.04 divided by 0.4 gives us 0.1 as the ratio. Plug into your sum formula. First term is 0.4 over 1 minus the ratio. You get 0.4 over 0.9. And as a fraction, if you multiply each by 10, you get 4/9. So your assignment is section 9.2. Try those problems, and we'll go over questions tomorrow.